Okay, hi, Anant. Maybe we can.
Anand, you want to bring your screen up?
Yes, I can share my screen. You can see it, right?
Yeah.
Okay. Yeah.
Hello, everyone. Welcome to the class. Anand is a very curious fellow, and he's currently hosted by Professor Francis Bach and Maxim Revitsky at UIUC. Before that, he completed his PhD in machine learning at Max Planck Institute under Professor Bernard Kolko. He did his BTech and MTech dual degree at IIT Frankfurt, and his research interest is in understanding problems in general machine learning theory and applications. More specifically, we have been looking at optimization theory, kernel measures, and theoretical foundations of machine learning. Well, what happened? And welcome, Anand, and
Thank you. So the title of today's talk would be SGD from the Lens of Markov process and Algorithmic Stability Perspective. Yeah, so I will start with a fascinating use case that I have been fascinated about. So this is an exoplanet discovery problem. Astronomers are interested in discovering if there is an exoplanet associated with a star. And if you search on internet machine learning and exoplanet discovery, you will see a lot of new articles from these famous labs and famous research journals that says basically deep learning and machine learning methods have been helpful in discovering exoplanets. And in the past 2 years or so, it's like more than 500 exoplanets have been discovered using deep learning techniques. Not only that.
How do we conclude that we discovered a new planet using machine learning?
Sorry?
How do we conclude through machine learning that we found a new planet? How does this work?
Oh, so basically, you have a receiver and you detect just the light coming from the star. So planets have no light. So what happens when a planet passes between the receiver and the star, the intensity goes down, and basically also there are like some noise, and then you see this pattern for a while and start to like check through like basically once you have preliminary investigations that okay there might be exoplanet, then you start to look carefully there. So this is the general pattern to discovering an exoplanet.
So are the ML methods used for screening or for the full discovery? So is it like the ML method is used to like draw through data to screen the candidates and then some?
So these articles at least say that they have been able to confirm it using machine learning methods.
Thanks.
So yeah, so not only that, so there are a lot of other tasks that seemed basically not very possible 15 years ago, and in recent years there have been some remarkable progress. For example, this AlphaGo, where a deep learning system beat the world champion, some protein folding, DeepMind has some remarkable results, autonomous cars and robotics. So what happened 15 years ago? People started to use like deep neural network from shallow, like they shifted to deep neural network from shallow neural network, and now they are basically shifting to more and more over parameterized models. And all these famous systems like that you hear and famous models that you hear about these days, they are basically a deep, highly over parameterized systems. So what changed? Of course, there are a few things. The large data set become available as internet became more accessible. GPU allowed faster training, and people also came up with like improved heuristics like dropout and like improved activation function that basically help in training deep neural network. But most importantly, people also learned how to use stochastic optimization algorithm to enable large-scale data training. What do I mean by that? So here is basically animation of a gradient descent update and a stochastic gradient descent update. Gradient descent update without the stochastic part has some problems. It's okay. So one thing is it's computationally expensive. It cannot be run on like very large scale data, and it has tendency to get stuck in local minima. On the other hand, stochastic gradient descent can escape local minima and saddle points because of the noise associated in it. And also it's computationally cheap. So the goal of this talk would be to understand the generalization in noisy stochastic gradient descent in the context of learning. And mostly, like when I say context of learning, like it also includes non-convex learning, because in the context of convex case, a lot of things have been already discovered. So question we ask, like, how to model the noise in SGD to explain the empirical behavior. Does noise in SGD help in achieving better generalization? And what kind of generalization bound we can expect when we model the noise? So let's come back to the same problem again. And I will try to explain how is it a prediction problem. So this is, in the ideal case, we would like the receiver to basically detect these kind of intensity when the planet is near the star, then the intensity drops, and it's very nice. But it's not actually the case. The signal that it receives is like some very noisy time series data. And the goal is to basically, on the basis of this intensity data on a time frame of t, you need to basically detect if there is an exoplanet system or not. So I will formulate now the least square regression problem. So you have observed data xi, yi, where xi is in this RT, where t is the time, a fixed time interval. Yi is like 0, 1, that already have been confirmed exoplanet system or not. And then on the basis of these data, you want to learn a model and predict a y for a new intensity data point x. And let's consider the linear model itself. So basically, you want to fit you want to learn a beta star and gamma star such that and predict y hat equals to beta star transpose gamma, beta star transpose x plus gamma star for a new data point x. What you do, you basically minimize, since you only have finitely many training samples, what you do, you want to like minimize the sum of squares of error. And you hope that this will also be okay.
Is it taking value in the interval 0, 1, or is it just taking two values 0 and 1?
Yeah, it's a good question. So right now I'm considering just two values 0, 1 because it's a prediction problem. But yeah, for more general tasks, this can be like a regression problem.
You can still do regression if yi takes two values?
I mean, you can still regress over this. I'm not saying it will be like very accurate or not, but you can still regress, right? We can still get some value. And then we can still threshold, right?
Okay.
So the goal is just to see that at the end of the day, we hope that like our model will predict okay for the new point x and y, point x, and will give a y hat that is closely related, like that is close to true level y. So let's move to a more general framework. So what we are interested in machine learning in general is minimizing the true population risk. We have a joint probability distribution pxy from which the data and label comes from. Model parameter vector theta, non-linear model function g. So what we are interested in minimizing the expected value of loss that takes x and y, and the loss is loss of y g theta x, where g theta x is basically your prediction by model g and parameter vector theta. Let's call this function f, but we don't have access to the true joint distribution. We only have access to this via finitely many samples. So all we have is like f at theta x, which is like average of lyi g theta xi. So we have only finitely many data points. So instead of minimizing true population risk, what we can do is we minimize like empirical risk. And when we minimize, we can basically deploy optimization algorithms. I would be focusing my discussion only on first order method because it's computationally cheap and cheaper than the higher order methods. So there are two sorts of method, like, okay, of course, I can find more categories, but like where you need at least to compute full gradient, or you need to compute stochastic gradient. So full gradient, you need to compute the full gradient of f hat theta and make an update. Eta here is the learning rate. And in stochastic gradient descent, you basically approximate this gradient of f hat theta t by some gt such that in expectant is still like gradient of f hat theta t. So there are problems associated with gradient descent. It's computationally expensive, and it only minimizes empirical risk. However, for stochastic gradient descent, it's computationally cheaper and also minimize population risk in streaming setting. So let's, since our talk is about stochastic gradient descent, so let's try to understand stochasticity and SGD. So this is the general update for SGD. So theta d plus 1 equals to theta minus eta gt, where zeta is the stochastic gradient. You can write it as like gradient descent update plus noise, where noise in expectation, the noise is 0. So in the case of empirical risk minimization, how do we achieve it? So we just, instead of computing the gradient on entire data set, we just randomly sample a batch size B and compute gradient on just those data points, average them out, and use it in our update. So if you see, it's basically just this term, the noise term, that's just sum of 0 mean ID random noise. Then if you assume finite variance, then our first guess is that from CLT, the noise should be approximately Gaussian. And in that case, you can model GT using basically 2 gradient plus noise, where noise is a sample from a Gaussian distribution, 0 mean Gaussian distribution. And that property has been exploited in many previous work. So what happens? Like when we write this as this SGD update as the gradient descent update plus noise, we can make the small size smaller, and basically this problem reduces to an SD. It's not very rigorous, but then you can basically, instead of studying the original problem, you can start to study SD and a small step size. And there are various recent works that have studied this dynamics. So, and they have been able to achieve impressive generalization result, convergence result for a class of non-convex function. And there are some basically some work that also relates this step size and batch size with the how much the variance should be and where what kind of minima your SGD converges to. So this basically is known as gradient Longevin dynamics. It's an important problem to study. It's an interesting phenomena because of its connection with SGD. Also some differential privacy connection, and definitely people in sampling, sampling this algorithm has been used a lot.
Anant, what's the wisdom here in terms of eta and the batch size? What are the optimal batch sizes to have? How does one think about these things?
So eta is the step size that basically just the discretization of this SD. So I don't get the problem. What's the question?
In some sense, one can make the batch very large, or one can make the batch very small. And you're saying somehow the batch size depends upon eta. So what's, what should the size of the batch be? What should eta be? How do we get emergence?
Yeah, so that's a good question. Basically, there has been studied on basically what should be the optimal batch size and like optimal step size. For convex case, this is like very clear. But for non-convex case, it's not so clear that what should be the optimal batch size. And also, like when you choose a batch size, you also have this computational limit in your mind. So you cannot compute if batch size too large, basically the it takes a lot of time to compute the stochastic gradient. So in practice, basically you need to take a lot of these things into account.
So what's in this case? What's the optimal batch size?
In what case? So I've not given a result for example, like in stochastic case, there is nothing like this. So but in some non-convex regime, I think it's I have seen some papers where it should be of the order of root n or something.
Root n.
Yeah. So yeah, this is the problem I described was gradient Longevin dynamics, which is again important problem because of its connection with sampling, differential privacy, and SGD based optimization. But there are some problems with Gaussian approximation. So this is a empirical observation. It's a non-convex landscape. There is a wide minima, there is a sharp minima. There are some empirical observations that flat minima generally is better, and SGD tend to converge to the flatter minima. There are also some theoretical explanation available by a pack-based bound. So the convergence results that I talked earlier, this work by Rejinsky and all, that requires basically in the worst case exponential of the order of exponential of D samples to reach to good enough minima where that they can generalize better. Momentum can accelerate the convergence, but still this curse of dimensionality is there. And also the empirical results that we observe in practice basically is in conflict with the meta-stability result, where the transition time depends exponentially on this gap H. Few years ago, Umut Simsekli did basically extensive experiment to observe that what is the tail, what is the noise behavior in stochastic gradient descent. So in this plot, if you look at this plot A and C, these are basically the norm of the stochastic gradient noise in the beginning of the iteration. So this is the plot A, and C is the random Gaussian vector. So in the beginning of the training, it looks much more like Gaussian. But this the moment you turn towards the end of the optimization problem, where you are like planning to stop it now, and there if you plot the histogram of stochastic gradient noise norm, and then it doesn't look like the Gaussian at all. If at all, it looks like more like a heavy tail, basically norm of a heavy tail vector, noise vector. And they have done very extensive experiment. I'm not going into detail, but in basically almost all the cases, they observe some heavy tail phenomena happening, and in almost no cases they have this Gaussian distribution kind of behavior. And heavy tail can arise in multiple ways. So one thing that basically very easy, if your data is heavy tail, then you can see some heavy tail behavior in the iterates. But here we don't assume that data is heavy tail. Even then, the heavy tail behavior can arise because of this multiplicative noise it has. So your noise keeps multiplying with the current state, and you can show at least in some least square case also, like simple problem like least square also, there would be like heavy tail phenomena. And in this case, bounded variance assumption is not always satisfied. So the moment this bounded variance assumption is not satisfied, your vanilla CLT does not apply. So you need to go for generalized CLT. And then generalized CLT say that like basically your convergence would be to alpha stable distribution. That's a heavy tail distribution. So I will come to heavy tail distribution in the next slide. So what is a heavy tail distribution? X has a heavy tail distribution if first thing is the variance is infinite. Sorry, go ahead.
So this tail you're talking about is the tail of the epsilon, right? So now it's not normal Gaussian. So you're not assuming. So this tail is about the tail of the error term in the.
Yeah, exactly right.
There's no SD anymore.
It's not. Sorry, I'm not able to hear you clearly. What did you say?
There's no stochastic differential equation anymore because there is no Brownian motion.
You get a Levy process.
I will come to it. So right now it's not Brownian motion. So that's basically clear that the behavior is not like a Brownian motion.
Okay.
So yeah, so X, a distribution X is heavy tail if the variance is infinite. In some cases, the mean can also be infinite. X is basically heavy tail of the order alpha if the tail decays at the rate like T2 power minus alpha. And alpha basically is the largest finite defined moment. For alpha less than 1, mean does not exist. Alpha stable distributions are class of heavy tail distribution where you don't know exact density function, but you have some form of characteristic function where these are parameters that relates to skew and mean, like if mean exists then mean, then if not, then something else. But there is some weird form of characteristic function, but no closed form density function exists.
Why is phi tan pi by 2?
Yeah, so it's basically if you derive characteristic function, then this is the case. I don't know why this.
I mean, you're saying it's going to infinity. I mean,
sorry,
it's infinite.
Yeah, so basically it would be infinite in some cases where I don't know. Maybe I just made some error, but I think. The variance blows for sure, and in some case mean blows as well. So there would be some term that probably is going to infinite. So I think I missed something. I'll check
Okay.
it here.
Okay. Got it.
So like Cauchy would be like alpha equal to 2, right?
Cauchy will be alpha equals to 1. So alpha equals to 2 is Gaussian. So the variance exists, and it's the Gaussian distribution. Yeah.
No, so for Gaussian, it is exponential, right? I mean, it's not alpha equal to 2. I mean, you're talking about this order of alpha, right? So
yeah, so alpha equals to 2 is Gaussian.
But it says probability that mod x greater than t is c over t to the power alpha. I mean, if t is large.
But this is only for alpha in 0 to 2.
I
so
see.
If alpha is this is like open interval. So if alpha equals to 2, that becomes the Gaussian distribution.
Okay.
Yes, then we move towards heavy tail analysis. That instead of modeling GT with a random Gaussian noise, we model it with like a standard alpha distribution. And again, we move to the limit where the step size is small. Then we have an STE, but this STE is like driven with Levy motion driven STE. So basically, it's a Levy motion driven STE. So there was this result in 2007 where it said the transition time from M1 to M2 does not depend exponentially on H. So basically, it can jump from M1 to M2, and that only depends polynomially on M1 and alpha. And this justifies some kind of jump behavior in SGD. That SGD also basically keeps jumping from, if you chain SGD, like it stuck in one minima for some time, and then it jumps from the one minima to another, and then this kind of behavior happens. And in a reasonable time. There are some recent interest in this problem because a lot of people observe this empirical in empirical experiments. So there are a series of empirical observation. Then there are also optimization work that was like as recent as was published in Cole 2023. Generalization error part is also like very few work, but there are some work. So for example, in Busby 2021, they basically work under very strong topological assumption on theta. Still, like they use like information theoretic methods to get the generalization error, but the relation between the alpha tail coefficient alpha and generalization error is not clear. And then in another work in Simsicli et al, they related to fractal dimension, but again, it's not concretely understood like how this tail behavior, like how this alpha is related to the generalization error. So what happens when the tail becomes heavier and like or larger? So in this, basically in the next part of the talk, I would be providing results from our two of recent work where we derive algorithmic stability bound for this SGE and also the discrete time processes, and try to put some light on this generalization behavior of this process with respect and how does it relate to alphas.
So Anant, in the training error, because you have heavy tails, presumably the convergence slows down, right? Although
right,
it might still give you better generalization. Is that the way to think about this?
Sorry, I missed the last part of your question. What?
Saying that, because your stochastic gradient iteration now has heavy tails, presumably convergence in the training data slows down, but you still get better generalization properties, out of sample properties.
Towards the end of the training, yes.
I see. That's the story.
Yeah, right. So basically, the story is something like this. So basically, the whole idea of this talk is again that like modeling this noise. Okay, I will also come to a part where I will say like this modeling the noise is important, but and also the modeling the noise with traditional Gaussian random variable is probably not the correct way. So in like scaling limit still okay, but probably like in the working is like where the things actually work is not okay.
So I have a question. So I'm just not trying to understand it. So you're saying the noise is non-Gaussian. So noise is heavy tail. So this means that sometimes this noise will be very large, right?
Right.
I mean,
right.
the estimate will be extremely large.
Right.
So the step sizes, I mean, the difference in the step sizes that you'll be taking, this is going to be large, right? It'll be taking Because the gradient is, the norm of the gradient is going to be large, right? Sometimes.
Yes.
Then you're going to take, larger step sizes. I mean, the larger step, the difference between two steps.
So, okay, so here we are only dealing with constant step size SGD. So
No.
large.
So let's say I fix my eta, but your gradient is large. The norm of the gradient is large, right?
Sure.
So that
So
is
yeah,
because your step size is large. So then
right.
how is it slowing down? So this is something that I don't understand. So why is it slowing down compared to a Gaussian noise?
Slowing
Gaussian
down.
noise, I understand that it is going to concentrate. But
Yeah, so slowing down, when I meant to slowing down, that means basically it will not be actually it will keep jumping from like one plateau to another plateau because of this noise, because of this basically large noise vector. And since this behavior only basically is realized towards the end of the process, so end of the process, this you don't care much about the convergence of the to the like training error, but you'll still like basically go from one minima that is basically sharp enough to the like one where like it's like not sharp, but it's more like a wide minima, flat minima kind of stuff.
so you're saying since it is a wide minima, I don't care. I mean, even if my the difference of the gradient is large.
Right.
I see. Okay, got it.
Okay, so yeah, and now basically now I will move to the result I provide in these two results. So let's discuss what's a generalization error. Basically, generalization error is the expected value of difference between the test and train error. There are multiple ways to get to study generalization error, and one of them is based on algorithmic stability, and we will be using this to study the generalization error in this context. So algorithmic stability, the concept goes long back to robust statistics. Also, there in 2005, it was famous paper by Bousquet on stability and generalization. But I'm using the definition from the recent paper by Maurice Hart, where he also basically includes an algorithm A in the definition. So an algorithm A is uniformly stable when you perturb the output a bit, and you can still bound the difference of the outcome of the loss function. So this is phi A is basically the difference of the outcome of the loss function when you have an input AX and AX hat, where X and X hat only differs on one data point. That's basically n data. It's a data set that consists of n data points. All the data points of X and X hat are same except one. So let's say the first data point differs. And if you can bound it, then you can bound the generalization error. And that's very intuitive that if you have a uniform bound here, then you can also have a uniform bound on the expected generalization error. There are also some problems associated with this algorithmic stability framework. You cannot obtain optimal high probability bound using this framework without any assumption. You have to assume like boundedness and stuff. But it's very simple framework, and you can obtain you can basically deploy this to get generalization bound for complex algorithm. For example, multipass SGD. There's no basically I don't know any good way to analyze multipass SGD without algorithmic stability. So now I come to this topic, SGD with heavy tail. We have this discrete time process where theta k plus 1 equals to theta k minus basically is gradient descent update with heavy tail noise. And we also have associated continuous time process. And now we will study generalization in these two processes under like different assumption on loss functions, f hat. So we start with a very simple problem where the problem reduces to OU process.
Are they noise IID or are they Markov?
Sorry?
Your noises in the previous slide, are they IID or are they Markov?
IID. That's a good question. I think Markov would have been much nicer, but right now it's IID.
It's IID, okay.
Yes. So we start with like very simple problem, least square, where fi theta is just half 1 by 2 theta transpose xi minus yi square. You can also for now assume yi 0. This will not basically make any difference in the result, but it will just like make the problem look a lot like an SDE problem. In that case, f hat theta x become 1 by 2 and theta transpose x theta. We also assume x transpose x is invertible, so strongly convex function. Very, very simple setting. We want to see like what can we say about this problem. So we have basically discrete time and continuous time process. As I discussed, this is heavy tail noise. So now let's proceed to the algorithmic stability bound. To get algorithmic stability, as I said, like we have to perturb the theta t by a bit, and that's why we have to define two processes. One is associated with the data set X, and one other is like data set X hat that differs by X only on one data point. So loss function is theta transpose X to absolute value of theta transpose X to the power P. I will describe later why I did choose P, general P in 1 and 2. And this is kind of the main part of the algorithmic stability term. So we need to compute the bound on.
Question here. So regarding this, so you're just jumping to this SDE. So is it like a rigorous result, or do you have a concentration bound in terms of high probability concentration around for finite step processes?
Yes, that's a good question. So basically, that's still an ongoing work that I have been doing. So we don't have. So we have some kind of result for basically phase retrieval problem, where we show some concentration, but in this part of talk we don't.
This is just analyzing the differential equation. Okay.
Yeah. So it's more like analyzing this differential equation with heavy tail noise and can.
Okay. Got it. Okay. Thank you.
So yeah. So this is the main term of the algorithmic stability term. So we want to analyze the difference of theta transpose X to the power P minus absolute value of theta hat transpose X to the power P, and it's very hard because like we don't have access, we don't have the finite variance, we don't have a density function. So what we can do is like we can just apply a bit of Fourier analysis and just transform this problem into studying the Fourier transform of X transpose, this function X transpose dot, and then the Fourier basically stability bound of the characteristic function. And we can do that. I will not go into the details how can we do it, but yeah, so as I said, like this stability is a supremum over like XX hat and okay, so here, and we can bound this term 1 and term 2. Term 1 is basically stability of the characteristic function, and term 2 is the Fourier transform of the absolute value of Fourier transform of the loss function, and we can bound both the terms. Then I will provide. I will jump directly to the result that like first major result of this paper that says that if alpha is between 1 and 2, and if you choose P higher than alpha, then this stability term will diverge. And that's obvious, intuitive also, because the highest moment that exists was alpha. So if you choose P greater than alpha, then you'll have some kind of divergence. When P equals to alpha equals to 2, then that's basically a Gaussian noise. You have stability result. And when P between 1 and alpha, so P is greater than 1 but less than alpha, then again you have some kind of stability result where you can say there is a optimal dependence on 1 by n. There is sigma mean is also optimal, and there is some function of alpha. And now we want to see like how does this alpha play a role in the generalization performance. Not only that, we also have a lower bound on this phi A that says that you're basically with constant probability this phi A is greater than this term. So it has like optimal dependence in alpha. So the bound is tight in alpha. And the process to get a lower bound is just to like reduce the problem to one-dimensional problem and get everything on the diagonal and try to construct this thing. So the conclusion is, since this bound is tight, so we try to plot the C alpha with respect to alpha, and this y-axis is generalization error, and you get to see that there is some alpha naught where you get the optimal generalization error. It's not only the plot; we also are able to prove that mathematically that C alpha is a non-monotonic function, and there is some alpha naught where you get the optimal value of this generalization bound, and that comes to this point that there is a particular choice of eta and b that gives the best test error. Why? Because in the experiments, when I showed you this experiment by Simsekli et al., they observed different tail behavior with respect to the choice of eta and b. What is the correct relation? That's not basically obvious and mathematically formalizable. But when they choose like different set of parameter for eta and the batch size, they get different tail behavior. So and this bound says that you don't get the same generalization error for all the tail coefficient. So there is some tail coefficient where you get the optimal generalization error, and that's very problem for very like basic problem, least square problem. Similar results also exist for discrete time processes. You follow the similar procedure. It's just a bit more complex in the basically algebra, but you can get similar stability upper bound and same takeaway that you have some kind of non-monotonic relation between alpha and the generalization error. But that was the case of just the least square. Okay, so this is also some experiments that we did that as you vary the variance of the data, it starts to show the more you like.
Can you please just again, what is alpha and what is P in all this?
Sorry?
What is alpha and what is P?
So P is the basically the loss function theta transpose x to the P. So the loss function that basically P is the basically how we measure our loss, and alpha is the basically the highest defined moment of the noise.
Okay, I see.
So yeah, so here are some experiments where when you start to basically increase the variance of the data, then you start to see some U-curve like behavior with respect to alpha. And this is a synthetic experiment. I will move to like now more real world experiment. We also did this experiment on a neural network where we estimated the basically coefficient of heavy tail and plotted the test accuracy with respect to coefficient of heavy tail. And we also see that as we move towards 2, this basically this error goes, accuracy goes down. So there is some point which is not 2 where we have like best test error sort of thing. So now in the next part of the talk, we will try to see that can we get this result that we got for this heavy tail SDE for a more general class of loss function.
So I have a question. So what is the source of this the alpha? I mean, it comes from the batches or it comes from something else?
It comes from the batch, and basically the major source of, like, even if you consider the least square setting, so there is a term of the noise that multiplies with state, like current states all the time. And if you do like basically this multiplicative noise results in this heavy tail. So of course the batch size has this dependence, basically has its effect on the coefficient of heavy tail behavior.
And the dependence on the batch size is clear, like how batch size influences alpha?
Yeah, no, it's basically it's not very clear currently.
So you'll have to learn that also maybe, and then tune.
Yeah, I mean that's basically, yeah. So as I said, like it's too many problems. Basically, no one understand what's happening. I mean, very little understanding is there about all these things. So it's not clear. There was some work by Peter Hysteric that I just said, like you can choose something like batch size of the order of square root of n or something. But still, I believe that work is not very rigorous and also deals with very specific setting of like PL inequality or something, if the PL inequality is satisfied.
I see. Okay, thank you.
So this is the case of general function. So the proof for the least square OU process was very constructive. We applied some Fourier analysis and able to bound the stability of characteristic function, and then we were able to bound the absolute value of Fourier transform. And this will not work for general class of functions because like you don't have the access to stationary distribution and any, like basically you don't have access to anything. So we'll need a new proof technique. So these are two processes, theta t and the perturb theta t, theta hat t. I will quickly define Wasserstein metric. That's basically infimum over gamma. D is a metric between x and y, and this basically if you minimize this integral over the set of all couplings, then you get Wasserstein p distance. For p equals to 1, there is this duality that says that this metric reduces to an integral probability matrix where supremum is over space of Lipschitz functions. And we will use this to get our bound. And why do I define it? That will be clear in this slide, that for a ellipsis loss, test loss function L, you can actually bound the expected generalization error with this Wasserstein algorithmic stability. And now this problem of getting generalization bound for reduces to just getting the Wasserstein stability bound. So now we are not dealing with the generalization error anymore. We are just like, we will be providing results for Wasserstein stability bound.
So you could have done this with least square error as well, right?
No, because least square error is not ellipsis.
I see.
So, okay, so there is basically tiny detail that I'm hiding. So here, the basic f hat where you run the gradient descent and the test function where you evaluate, these are two different things. And that's this concept of surrogate loss and true loss. So it's like saying you are interested in 0-1 loss, but you still like minimize the hinge loss. So that kind of thing. Is it clear?
Sure.
So these are the assumptions on basically the function. So one is like a smooth, of course. Without smoothness, I don't know what to do. And then dissipativity condition. This also includes some class of non-convex function. And we will be providing results for this. So I will not go into the detail of the proof, but basically the proof relies heavily on exploiting this duality of Wasserstein one distance, and then also controlling this fractional Laplacian operator in some way. But we are able to get this Wasserstein stability bound between mu and mu hat, where mu is the unique invariant distribution of theta t, and mu hat is the invariant distribution of theta hat t. And this rho xn and x hat n is again they are just like distance between these data set xn and x hat n that only differ on one data point. So it's order of 1 by n. And that basically will give you generalization error bound, expected generalization error bound. You can also get the results for discrete processes. Nothing else to do because this discretization error was studied very recently for this process. So we just need to add this to the continuous time process, and we get this Wasserstein stability bound for the discretization error. Dependence on alpha. Now basically I put these two images side by side. I plot. Okay, so this is G alpha D is some term that has alpha dependence, but of course like it's proper. Right now it looks skewed, but with proper scaling and stuff, it's not so skewed. And again, we can basically plot and also show that this function is also non-monotonic. This bound is not so tight, but at least in the upper bound it looks like this has some non-monotonic. Alpha has some non-monotonic relation with the generalization error.
So dimension here, small d.
So d is the dimension of the problem.
Okay. So d equal to 20 is very small, right?
Right.
Typically, don't you have much higher dimensions involved?
Yeah. For all higher dimensions, you get the same behavior. So it's so that we prove mathematically in the paper. It just I plotted few.
I see.
So summary so far is basically we experimentally discuss some results that say that modeling the noise using Gaussian random variable is not probably the correct thing to do. So perhaps we should move more towards heavy tail noise. And in heavy tail case, we took two specific cases. Like one is very specific least square case, study the generalization error and see the behavior of generalization error with respect to alpha. And now in the second part, like we consider like more general loss function that also includes some class of non-convex function. And we study the generalization error via studying the Wasserstein algorithmic stability. Now I will just move to this quickly this part of talk where I will quickly describe that. Okay, so can we unify? So the problem is like for every problem of this nature, you need to devise a new proof technique to get Wasserstein stability bound. And in this part, I will quickly show that there can be the result from Markov chain perturbation theory that can be used to get a unified framework.
So Anant, can you hear me now?
Yes, yes, yes.
So in the two different loss functions that you had, there's this, the least squared and the other one with this Wasserstein technology. What's the qualitative difference in conclusions that you're making? Are you saying the same thing or something very different?
Okay, I think the conclusion is basically same, but since it was the least square, we were also able to derive the lower bound and study the process very exactly. But for this more general case, it's hard to study the lower bound. But the conclusion is still the same, that you have some generalization performance that is of the order, like expected generalization error is of the order of like 1 by n or something. That also was seen in the least square case. And then you have similar, basically non-monotonic relation with respect to alpha.
So how to interpret this non-monotonic relation with respect to alpha? What's the intuition behind it? How do you explain it?
So basically, in a way, it says that, okay, if there was a control between the law of SGD traits and this heavy tail SD, and it was observed in experiment that this was basically the tail coefficient depends on the choice of eta, that is step size and batch size. So for a particular choice of step size and batch size, you will get a best test performance. So in a very non-rigorous way, we can say it like this.
Okay. I see. Good.
So in this part, basically, we will just describe you a very recent result that we are going to present in this new RIPS, that where we use this result from perturbation theory for Markov chains to get a uniform, to get a unified framework to get Wasserstein algorithmic stability bound. So SGD constant size SGD is a Markov chain. We again consider like two sequences, theta t plus 1 equals to theta t minus eta gt, and then their perturbation of this. So there was this result like 5 years ago in the Rudolph, that under that study, like what, okay, so small differences in the transition probability of Markov chains, how does it reflect in differences between their distribution? And for this result to hold, that one of the Markov chains should be Wasserstein ergodic. And we use this result to basically derive Wasserstein stability bound. Again, we start with very simple case where we have a least square SGD update. First step is to establish the geometric ergodicity of the Markov process, that we can do easily for the least square. Second would be to construct a Lyapunov function. I mean, there is as tons of Lyapunov function that has been constructed in optimization theory to study different optimization methods. And then third is basically to estimate the perturbation gap of the Lyapunov function. This is you just like need to show that it's bounded. And these are the results that you then can get without using any stochastic differential equation theory. You can bound the Wasserstein algorithmic stability for a square loss SGD. You can apply similar techniques to get the Wasserstein algorithmic stability bound for strongly convex loss SGD. And we also provide this bound for non-convex function. This is Markov chain stability bound. The results are again similar. It's just a bit more complex to show because it's not easy to show the Wasserstein ergodicity in this case. But the point to notice that this result does not hold if you don't add noise here. So we have to add noise here to make this result work for the non-convex functions. That basically hints also that why this noise modeling of the noise in SGD is necessary in some way to get some result for a general class of non-convex function. This is a bonus result that we, of course, we also like we have more results in this paper that where we extend this perturbation theory for like subgeometric ergodicity and stuff. But this bonus result says that can we use the same approach to provide Wasserstein stability bound for vanilla SGD, and the answer is no. That if we don't have noise, we cannot show the geometric ergodicity. And then using some other technique, we show that we only manage to show some bound for SGD on the class of non-convex function where it does not vanish asymptotically. So there is some dependence on K by M or something that is going to remain. So we don't have a lower bound. So I don't want to make any hard claim, but it looks like basically it's necessary to add noise or basically model noise in SGD to get a meaningful point for non-convex problem. Summary so far is like there are two parts of this talk where in one part I describe how to study the SGD with heavy tail, the generalization in the SGD with heavy tail, and what is the relation what is its relation with SGD training. In the second part of this talk, we gave this unified framework to get Wasserstein's algorithmic bound for noisy SGD update. But there are a lot of open questions. Basically, what we could answer is like also like not even like tip of the iceberg. So first thing, like how do we get control between the stationary distribution of SGD and the model ST? And that's basically one problem that I'm kind of interested in and looking for, not for general class of function, but only for phase retrieval right now. The other things are like, can you basically get results for more general class of non-convex function, or like apply this to specific problems like neural network or phase retrieval and these kind of things. So these were like the main reference for the talk. This based on these three works that was presented at ALT, ICML, and NeurIPS. So I will also quickly discuss my research chart that most of the time I